Hello everybody, and welcome to Hypothetical Science. Now, in hypothetical science, I'm exploring a hypothesis that's very, very simple, which is atoms and galaxies are exactly alike. And what that means, since galaxies are made from atoms, then if atoms are exactly like galaxies, they must then be made from smaller versions of themselves. So it's just like the Russian dolls thing. You open the big doll and there's a smaller doll. You open the smaller doll, there's another smaller doll. And it's turtles all the way down. So, using this hypothesis that galaxies and atoms are exactly the same, I'd like to talk a little more about gravity being a push. Now, all the schools teach that push gravity has been debunked. So why was it debunked? Well, there are four main reasons why it was debunked. And the galaxy model for the atom gets around those four reasons. The first reason is, well, if all matter is absorbing this omnidirectional flux of ultramundane particles, then the matter will overheat. And they calculated that that would happen very quickly. However, in the galaxy model, it's the atoms themselves that are putting out the push, that are pushing on the other atoms. And so it's an equal energy exchange. The matter itself is creating the energy, and there's never going to be any more energy. It just gets recycled. So the second reason that push gravity was debunked was because if you've got this average omnidirectional push in space, and then I'm going a certain direction faster than you are, then I should be getting hit by more of this flux from the direction that I'm going. So my gravity in that direction should change. And experiments have shown that it doesn't, so that's supposed to be a debunk. However, in the galaxy model, this gravitational push that's coming from matter is a radiation which is given off. And the radiation is being absorbed according to its frequency. So if the matter is going fast in a certain direction, it doesn't hit more gravitational push. It just hits a gravitational push that is shifted in frequency. And the matter then just selects the frequency that matches it. And there's no change in its gravity. So, if the gravitational push is a radiation, then you don't get that raindrops effect problem. And the third reason that they debunked push gravity was what they called ecliptic shielding. Now, in an eclipse, where there's a planet in between two other large bodies, if you have push gravity, then that planet should be shielded from gravity from both sides, and you should see a change in the planet's gravity. And so they look for that during eclipses, and there is no change, except for something called the LA effect, which happens It happens slightly and in a hard to predict manner. There's some kind of an effect, but it's not from being shielded from the gravity. So why that doesn't happen with this kind of push gravity is because it's the matter itself that's giving off the push. So the planet that's in between the two other large bodies, those two large bodies are shielding it from the push coming towards it, but they're also emitting push towards it. So there's no lack of push that happens during the eclipse. There's going to be some stirring kind of around the edges, which is, I think, what that LA effect is showing. So yeah, that's the third reason it's debunked. And then the other reason it was debunked is kind of silly. It's like, well, the ultramundane particles have to be extremely, extremely fast, and they have to be extremely, extremely small so that most of them go right through the matter and only some of them get stopped by the matter. And yeah, when we're talking about electrons giving off radiation because of their internal processes, those are very small, very numerous, and very fast bits of radiation. So that would definitely qualify. But let's talk about dark matter. So the universe is fractal. The universe is fractal. Galaxies are made out of atoms, which are just like the galaxies. So the atoms are made out of smaller atoms that are just like them. And those smaller atoms are what make up space. Those smaller atoms and, all of the things that those smaller atoms make, like smaller planets, smaller stars, smaller microbes, smaller viruses. So galaxies are like 10 to the 21 meters. Atoms are 10 to the 31 times smaller at 10 to the minus 10 meters. So if you go another minus 31, you get the size of space atoms is 10 to the minus 41 meters. So that's 10 million times smaller than the Planck limit. And stars, the stars that make up electrons, are going to be in and around 10 to the minus 22 meters. 10 to the minus 20 to 10 to the minus 22 meters are going to be the size of those stars. Those are the stars that make up electrons. Those would be the largest material expressions of the atoms that make up space. So space is an actual medium. Space has energy. It has just as much energy as matter, maybe more. But it's just so finely divided. It's just so small. So what happens with space is that you can set up currents in it. And what dark matter is galaxies, disk galaxies, using their most efficient way of movement, which is to rotate once every time they precess twice. And what that makes them able to do is for opposite sides to follow each other. So all of the opposites in the galaxy are following each other. So it's a huge energy advantage. And that's why the reason it's an energy advantage is because they draft each other, and they're able to draft each other because space is a medium. And so it sets up a current in space. And that current is your dark matter. And they found that irregular galaxies don't exhibit the dark matter effect. And the reason they don't exhibit the dark matter effect is because they don't have disk symmetry. They are unable to do the 1 to 2 rows movement where opposites follow. So that's all dark matter is. Dark matter is actually currents set up in the smaller matter of space, according to this hypothesis. So yeah, let me know what you think, dark matter, and why push gravity is possible.